So let's start the recording. So we rewound a little bit here. We are back to the slides that actually introduce the pseudocode for the evolutionary algorithm that we talked about, okay? So the previous slides before that were introducing the general idea of crossover, mutation, selection, etc. Okay, so there are more details there. This is pretty much an outline of what you have to implement. And again, one of the early questions that I mentioned last time was, you know, do you guys need to do something about the design of this algorithm? The answer is clearly no. Take the algorithm as it is given to you, okay? Just make sure that you implement it using the techniques that we are discussing in this class, okay? Meaning inheritance, etc. And then very soon we're going to have more fun techniques to implement. Okay, so what do we have? What do we have in this algorithm? Just quick reminder. The first step is to initialize your initial population. So the bio jargon is coming in here, okay? Initialize your initial population of candidate solution. So for the problems we are going to tackle, the one max problem, these are going to be fixed size, random binary vectors, okay? So let's say that the population size is 50. I'm going to have 50, 10-bit long maybe. All of those numbers are going to be given to you, okay? But 50 is the population size, 10 is the length of the binary vector for the one max problem. Okay, so I have 50, 10-bit long random Boolean vectors, okay? Then you compute immediately the fitness for every candidate solution in that random set. So the fitness function, that's spooky music there. The fitness function is remind you the one max. Okay, for our first implementation, fitness is trivial. We count the number of 1 in one of those binary fixed size vector, and that gives us a fitness. The higher the fitness value, the better the candidate solution. Hopefully, after a few iterations, after a few generations, we are going to see appearing individuals, candidate solutions that have more and more bits set to 1, okay, in their vector. So that's the initial step. You do that one time, and then you move on to the cycle that's going to repeat itself every generation. So again, the maximum number of generations is going to be given to you as well. Okay, so I'll say, for example, okay, let's try to solve a 10-bit long one max problem, so that gives you the size of each candidate solution, with a population of 50, and we're going to run that for 500 generations. So there's nothing you can break by setting those numbers yourself. Okay, the only thing is that if you don't give enough generation, then the quality of solution is going to improve slowly and never reach, you know, the optimal solution, which is having 1, 1, 1, 1, 1. Okay, if you give a population that's too small, you are going to need more generation to find the solution. So there is kind of a balance there, and the overarching tuning parameter is that the longer your bit string, the more generation and the larger population size is going to take the algorithm to find a solution, to find the optimal solution. Okay, it's going to find plenty of solution in between, but they are going to be intermediate. Okay, so what do you do each generation? Well, each generation you select 2 individuals in your current population as the parent. Okay, so you use the selection algorithm that we discussed. More specifically, the one I want you to implement first is very easy. It's a K tournament, okay? We talked about it already. K tournament, again, a parameter, the value for K. In our case, we're going to use K equal 2. A 2 tournament means that you pick 2 random individuals from the population, and you keep the best one, the best of the 2, the one with the highest fitness, okay? That's a selection method. Now you have 1 parent. Then second parent you need to select. You pick 2 from the population, so you can pick again one that you previously selected, that's allowed, and then you take the best, and there you go, you have your second parent, okay? So the funny thing about K tournament, it has some interesting properties as far as evolutionary computation goes, but we are not here to talk about that. The only thing I want to point out is that the value of K, again, that's something that you can play with. 2 is standard, but you're not going to break anything. The idea behind the value of K is to give you a way to control selective pressure. So let's say that we have a population of 50 candidate solution, okay? Well, what happens if we set K to 50? Then we always select the best individual in the population, right? We take the 50 of them, take the best. If we set K equal 1, we select 1, we take it. So it's random. So between k equal 1 and k equals the population size, you have a way to tune here, okay, to make it more and more selective. Play with it, see what happens. Okay, the rule of thumb is you have to be careful about being too selective. Otherwise, in complicated problem, you converge to a suboptimal solution. But here with the 1 max, it should not be a big problem. What's next? Then after you selected those two parents, P1 and P2, you are going to modify them. Okay, that's what evolution is about. Evolution is about modification, random modification most of the time, and then selective pressure to keep the good modifications. So we already selected two parents that on average are going to be decent, okay? And then we apply crossover to them. So crossover, I refer you to the previous slide, okay? You cut the segment anywhere, you cut the binary vector, sorry, anywhere in order to obtain two segments. So you don't have to cut it in the middle as illustrated in the previous slide. You can cut it on any side, okay? And then you exchange half of the binary vector, and that's it. So that's called a 1-point crossover. And I'm mentioning, the different variants, because for each single operator in this algorithm, there is a list of variants that is incredible, which makes it good for us, because that means that there are a lot of things to parameter, and there can be different objects that we can use, to implement a crossover operator, and then subclass the class and have another subclass that implements a variant of the crossover operator, okay? So that's what's interesting for us, not the detail of the algorithm itself. So once we apply crossover, 1-point crossover, we obtain two offsprings, O1, O2, let's call them that, and then both of them are going to undergo mutation. Again, prepare your code. You're going to have different version of mutation, different version of crossover. You need to be able to extend your code as the requirement evolve, okay, no pun intended. But you're going to take O1, O2 and apply the most basic mutation version, which is a per gene mutation version. So again, the lingo, the biology lingo, what we refer sometimes as a gene is just one of the bits in the candidate solution. Each bit is kind of like a gene in a chromosome, okay? So traduction, you go over your entire vector for one candidate solution, and for each bit of information, pretty much you flip a coin. Let's say you have 70% chance to mutate. Well, 70% of the time you flip it. 0, 1, 1, 0. That's it. Okay? So that's, again, the simplest mutation operator we can implement, but there can be other ones. So you apply this to O1, you apply this to O2, and don't worry, by the way, if you implement something that differs a little bit from the basic version that I give you, it's not a big deal. Again, our goal is not to do experimentation with the algorithm. Our goal is just to have you implement a version of this algorithm, even if there are a few errors in it, okay, that is capable to be extended. We are going to extend the heck out of this, okay? What's next? Once you have your two offspring, O1, O2, they have undergone mutation, potentially. Now you're going to compute their fitness again. So you have new version, new candidate solution that you generated from P1 and P2, okay, applying this crossover and mutation steps, and now you are going to compute their fitness so you know how good they are. And that's going to help you re-inject them into the population. So remember my population for this particular generation, I took two individuals, they are still in the population, right? I just made two copies of parent 1, parent 2, messed around with them. Now I want to re-inject the offspring in the population. So what we're going to do, again here, we're going to do something very simple. There is another selection, technically, that takes place here, Who is going to get killed? Who in the population is going to get outed, and replaced by O1? And then we do the same thing for O2. Well, in this case, what we're going to do is we're going to do selection of the worst. So you look at your population, you take the lowest fitness individual, and that's the individual that's going to be replaced by O1. Once you did that, you look again at your population that contains O1 this time, and you locate the worst individual again, which could be O1, okay? And you replace it by O2. And that's it, you're done, okay? All right, so this is the outline of the evolutionary algorithm. that I covered, like I said, a little fast last time. Another thing that I covered a little bit fast is, well, the detail for breeding here, I think we are okay on it. I don't want to go again too fast, but let's pause a minute. Are there any questions about how the selection works? Or my explanation was clear enough so far? We're good? Okay. So we're going to skip a little because the 2 slides that come here, I just repeat pretty much of what I explained when we were on the full outline. So 2 types of selection, breeding and replacement. Okay, I covered that. And then apply crossover. Okay, we covered that. Apply mutation, we covered that. So the other thing that I went a little bit fast over last time was, what is the outcome of this algorithm? So let's say I ask you, solve a 100 bits 1 max problem. So 100 bits is the length of the candidate solutions. Use a population size of your choice. Use the max number of generation of your choice. Experiment a little, figure out numbers that seem to work. Okay, you know what you need to converge to. You need to converge to an individual that has 1, 1, 1, 1, 1, 1 everywhere. Okay, so what is the outcome of the algorithm? Well, once you reach the max generation number, okay, you stop. You look into your population. You locate the best individual, the one with the highest fitness. In some cases, in some problems, you can have 2 different individuals or more that have the highest fitness value, the same highest fitness value. Okay, with 1 max, nah, that cannot happen. Well, that can happen if you don't converge properly, but we'll see about that. Bottom line is you pick the best, the highest fitness individual in your population, and you display them, and that's it. That's the outcome of your program, okay, of your algorithm. Remember, this is an optimization algorithm, so somebody comes to you with a problem, you run this algorithm for a certain amount of time, and then you tell them, well, I let this algorithm run for 2 days, and this is the best solution that it can come up with. And then we take that generally and we discuss it with the clients, and we try to figure out, if this is a decent solution or not for them. So that's your outcome. Just a side note about that, there is another thing that you can do to check if your algorithm is working or converging, I should say actually. You can actually have your algorithm just display on the console or write into a file, whatever you want, okay, the value of the current generation, so generation 1, and next to it the value of the best fitness. You can even dump, if you want on the screen, the bits that compose the best individual in the population, so you can see them, evolve. But you can dump like that for each generation the current value of the best fitness, the best quality found so far, and then the individual. If you do that, there are all sorts of tools. I don't know what you are familiar with, but if you are familiar with the R programming language, for example, even if you are familiar with Excel, there are all sorts of tools that could take, a simple output like this, a simple file like this, and give you a plot. So the kind of plot that we get with this, they look like that. Okay, they look like that because they are averaged. If you do the plot only for 1 run of the algorithm, the curves are going to be a lot smoother. But what we did here, we were trying to compare 2 variants. I told you that there are so many variants, right, of the evolutionary algorithm. Well, most of the time you want to determine which variant is actually the best for a class of problem, or even for one specific problem. So in this case, we would have applied the same algorithm, the green algorithm, for example, many times, like 50 times, to the same problem. And every time we generate the kind of data that I just mentioned. But then what we do at the end, this is where Excel or R or any sort of processing tool there comes in handy. What we did at the end is, after running 50 times and getting 50 output, we looked at generation 1 in those 50 trials, in those 50 runs, and we computed the average. And we started doing some statistics, okay? Maybe we looked at the standard deviation, stuff like that. So the idea here is that when you are trying to figure out, okay, what variant of this algorithm I should use for this type of problem, you are going to often do this kind of stuff, okay? And the advantage is that whether you average the behavior, like the average best fitness found for each generation, over 50 trial, for example, or whether you look at a curve that represents only 1 run of the algorithm, okay? you can use that also to debug your code. That curve, with what we are using right now, let me think real quick. Yeah, with the default method that I told you to use right now, for example, you should never see those curves plummet. You should never see them go down, because then your algorithm is not actually improving anything. It's actively searching for something that is worse. Okay, so same thing. You should not observe plateau, because this is a simple problem. A plateau is when you start converging, you go up, 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 and then you stagnate. You stagnate for like a long number of generations, okay? So if you observe any things like that, come to us, okay? Come to me, come to the TA. We'll help you get the algorithm to the point that it works. We do not care if it works well or if it's like really like sluggish and whatnot, okay? Again, that's not our main focus, but this gives you an idea of what to look for if you have problem getting this whole thing to work, okay? And just a quick remark, in practice, if you compare two algorithms like that, so you are going to have to do many runs, many trials, okay? This is not a stats class, but you guys should have heard at some point of the central limit theorems, things like that, okay? If you want to compare the averages between two samples, well, you better have a minimum number of repetition, right, of your experiment. So in this case, we took 50, which generally is sufficient. So you look at those curves, you say, I had one version of the algorithm, the green curve, and then another version, and wow, the blue curve shows that the blue algorithm is really outperforming the green one. It converges to a better solution faster. And then when you start getting into those comparisons, the only thing I want to point out without going in detail is that you have to be really careful. It's useful to have a friend that is really an ace in statistics that can catch you when you start doing things that are really unholy with statistics. Like, for example, comparing those two curves is really not the right approach. Okay? Most of the time, we try to have one number that represents the average performance, for example, on the last Phazon generation or on the whole set of generation. And then we're in a situation where we have to compare the mean of two samples. And this is much more comfortable to do, things like statistical significance test. If you have two curves like that to compare, you can still go and do some things like plotting the standard error, for each generation. And that allows you to realize very visually that when you have the standard error overlapping between the two curves, well, when you are, let me grab the laser pointer here, when you are, for example, here, when you are like almost done with your run, you really don't know, you know that on average the blue one is above the green one, okay, the blue algorithm outperforms the green algorithm, but really there is such a huge variation here and here that they overlap. So if somebody comes to you and say, well, I have this problem to solve, I want your best algorithm, and I'm going to run it one time on my problem. So this person is not interested in studying, which variant is better on average. They just want to use it one time. Which one do you recommend? It's really not clear in that case. Okay. So just a side remark about the stochastic nature, pretty much, of those algorithms, which makes them really fun to debug. All right. Now let's branch back where we stopped last time, which was just an example, okay, a run of an algorithm to give you an idea of what happened every generation. So we are back in Rabbitland, okay. So Rabbitland is our knapsack problem, right? Remember, we have 4 objects. Each of them has a value represented by a number of hearts and has a weight. And we have a bag that can contain only up to a certain limit weight. So packing everything is really a bad idea. The X here, the green X represents the fact that we take this object in the backpack, the red that we do not take this object. Each of those vertical series of 4 green and red X's is one of our candidate solution. Okay, so we have a population here of 3. Just because it fits on the slides, really, this is a bit tiny for a population. But so this first candidate solution says, I do not pack the first object, do not pack the second or the third, I pack only the fourth. Okay. So based on that, based on the definition of the knapsack problem that is always given to you, that's a problem you need to solve. You don't need to invent the problem. You can say that this solution has a value of 2. 2 is just the value of the last object, because this is the last one, the only one that we packed. And it's okay insofar that it doesn't go overweight. And then this solution here has a better value, 4, okay, but we take actually 2 objects. And it's still okay with the weight limit. And then there's solution here, which is kind of trivial. It's okay, pack everything, you maximize the value, right? Yes, but you violate the constraint for the weight. So based on the knapsack problem, this is not acceptable. Okay, so now we're going to apply this pseudocode that we talked about, okay? So let's start with the selection for breeding. So I'm picking an individual. How do I pick it? K tournament, K equal 2. So I really pick two individuals, compare them, retain the best. So let's say that in this case, I picked twice this guy, so I ended up selecting it, like pretty much like if K was 1, okay? It's purely random. Then I select another individual. So again, I do a K tournament, K equal 2, and this is what I get. This is the individual I get. So selection for breeding, done. Notice that I didn't remove those individuals from the population, okay? That's a mistake a lot of people do the first time they implement an evolutionary algorithm. So now that I have those two individuals, those parents P1 and P2, I go for crossover. So in this case, the crossover is going to cut right here, okay, after the first bit. I told you that can be random. In the slide, it was always the middle, but it doesn't have to be always the middle. So you determine randomly where you're going to cut, then you make your cut. Once you make your cut, you are going to swap the two halves. I mean, it's not really necessarily a half, but the two segment, the bottom segment of the two solutions. And then we go for mutation. So here's our mutation. In this case, we are going to, I think this example is showing a different mutation operator. In this case, the mutation operator is pick one of the bits at random and flip it, and that's it. So we flip one bit per candidate solution, okay? So that's another variant, yeah. Yes. The question is, on the first step of selection for breeding, can we obtain two parents that are the same? And yeah, the answer is yeah. As a matter of fact, as you progress through the generation, okay, what's going to happen is that the good parts, the good segment in each individual are going to multiply in the population. So for example, if you looked at the initial population, maybe 50% of candidate solution start with a 1 and 50% start with a 0. But as you progressively improving the quality of your solution, the percentage of candidate solution that start with a 1 is going to increase. Like if we're talking about the 1 max problem, okay, I should have made that clear, sorry. If we're talking about the 1 max problem, where the best solution is 1s everywhere, the number of 1 in each candidate solution increase as time passes, okay? So if you project that really to the extreme, that means that our last generation in the 1 max problem should have a bunch of candidate solution. And when I say a bunch, I mean 99% of your population should comprise solutions that have all 1s. That's when you converge. You not only found the best solution. You not only found one candidate solution in your population that is 1s everywhere, but once it appears, it spreads through the population. Just like saying that good genes, in an evolutionary system, natural system, would spread in the population. Okay, genes that have a high chance of survival. Same thing is going to happen here. So as you progress and as you reach the last of your generation, that case that you brought up is going to happen more and more often. We're going to end up picking two parents, P1 and P2, that are actually the same and that are very high fitness individual, if not the highest possible fitness individual. So corollary to that, crossover is useful at the beginning of your run, but as you converge, crossover is crap. Okay, because if you have the same two parents, you can cut them however you want. You exchange, bits between the two, but since they are the same, it's not going to do anything. So at the beginning of your run, the crossover is essential. Towards the end of the run, the mutation is the only thing that actually introduces diversity. Okay, so I'll try to refrain from going into too many details there, but that was a good question there. Okay, so once we are done with crossover and mutation, selection for replacement, again, we have those two new offspring, okay? We need to re-inject them in the population. So we're going to use the same technique that I already described, okay? In that case, we're not going to use K-tournament, we are going to use pick the worst in the population, replace it by the first offspring, then pick the worst again, replace it by the second offspring. Bottom line, those two guys are going to end up being re-injected in the population, and we are going to iterate this over and over and over again. So generation 1, maybe our best fitness was 4, as you can see at the bottom left of the screen there. Well, if we were dumping this information every generation, then we could graph the progress of our algorithm, right? So second generation, now the best individual we have, after doing crossover mutation, blah, 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 is 4. So we went from 2 to 4, okay? And then we keep going like this. And what we are going to obtain is generally, if the problem is relatively simple, it's generally an asymptotic curve. Now, the EA version, the evolutionary algorithm version we're using is very basic. Okay, it's not trying to do anything smart. So asymptotic means that it's easy to improve quality at the beginning. So your algorithm looks like it's really working, but then it takes you an insane amount of generations to maybe hit that optimum. So in the knapsack problem, I don't remember which 4-bit vector would be the optimum, but in 1 max, hitting that 1, 1, 1, 1, 1 everywhere, that may take a little bit of time. You might have, if your vector size is 10 bits, for example, you might reach very fast 8 or 9 fitness value out of 10. And then going from 9 to 10 might take quite a number of generations. So you'll have a chance to see that when you run actually your code, okay? Back to our OOP techniques. That's what we are really, really interested in this course, right? So we're going to try to solve 1 max. Candidate solution could be objects, okay? So I say could because everything I'm going to talk about right now is just suggestion. Like I said last time, I want to encourage you to go wild with your designs, okay? So if you really do not know where to start, well, here's a starting point. Your candidate solution, each candidate solution in the population could be an object. So you would have a class candidate solution. If you go that route, the advantage is that, well, crossover and mutations are operations that apply to candidate solutions. So they could fit, in that class, okay? Just make sure that as you have to implement different variants of crossover and mutation, well, you understand that you're going to have to have different variants in the method of that class. Okay. For that reason, some of you might actually say, well, forget it. I might use candidate solution as a class, but I'm going to also have a class that represents mutation operator in general, a class that represents crossover operator in general. Okay. So if you do that kind of stuff, you're going to probably end up with classes that have like 1 method or something like that. The bad news is that from the OOP perspective, you're going to scratch your head at some point and say, my design is really weird, especially when you compare it to our classmate. He's already laughing because from a functional perspective, then the transition to a functional design is going to be much easier because then you're going to realize, wow, I have 1 method in that entire class. Maybe I can get rid of that class, okay? So like I said, whichever route you go really doesn't matter because you're going to learn something during the process, okay, during the journey. So over basic suggestion, population could be a class too, okay, could be a container. If you start thinking that way, then the selection operations, selection for breeding, selection for replacement, are operations that take place at the level of an entire population, right? So you could implement them in that class. Okay, the idea of having a container class for population, right now implement it as an array. Okay, as soon as we cover collection, or if you're already familiar with collection, go ahead and use collection. But when we cover collection, the first thing we're going to do is we're going to revisit this and say, okay, whatever type of container you use for your population, okay, to all those candidate solution. Now let's try to use Java standard collection instead, okay? And let's try to use a sort method in the collection because when you want to find the worst individual or the best individual, or even the nth best individual or nth worst, this problem can very easily be solved by sorting the thing. Okay, so at that point, I don't want you right now, to re-implement a sort algorithm and stuff like that. That's a waste of time. This is not a data structure class. But as soon as we get into collection, then sorting is just a matter of understanding, how to make your collection sortable. So that's going to be relevant to this course. So I'm trying to give you ideas of the kind of changes that are, in our near future. So that every time we learn to do something new, then we go back and we improve a little bit this algorithm. Okay, so we're almost done. Another thing that is important to start working on from the get-go, so that means right now, is dealing with the parameters, all those parameters that I mentioned for this algorithm. And there are a ton of them, okay? Which is good, because that's going to force us to have a parameter file, which is going to immediately connect to what we're going to do in metaprogramming, okay? We're going to, like in the next 1 or 2 sessions, we're going to deal with metaprogramming, and we're going to learn to handle this kind of parameterized algorithm very, very nicely, okay? So there's a reason to the madness here. So this slide lists pretty much, I think, all of the parameters that we talked about so far. So you are going to, and I really don't care about the names that much, but except if you have a big problem with one of those names, go with that. N can be, for example, our length for the candidate solution bits, bit vectors. So we're going to solve 1 max. So this would mean we are trying to solve 1 max on 500 bits. Population size, self-explanatory. Max generation, self-explanatory. I want you to have, and this could be another class also, a class algorithm, okay? Let's say that we want to change the order in which we do selection, crossover, mutation. We want to add a step. We want to remove a step. We want to do things like that. Then you have to have like somewhere where you have this flow, this pseudocode implemented, right? So if you make it into a class, that means that you can have different variant again. All right, just a suggestion. But in this example, I'm using the fact that, yes, I have a parameter that's going to be called algorithm. And well, all I'm going to implement for now is this basic evolutionary algorithm. That's the name I'm going to put in the configuration file, and that's going to correspond to what we discussed. The candidate solution, well, same thing. If you have several classes for your candidate solution, okay, right now we're talking about only using binary fixed vector. But in the future, I want to be able to go to that configuration file and say I want an integer fixed vector. So I would like 500 integers, and then I would need another parameter to tell me, what is the range of value for each of the integer, right? But I want to be able to change that. So again, this is to give you an idea of what's coming in the future. The fitness, well, yes, I want 1 max. So it's a good idea to have a class called problem or environment or whatever you want to call it that represents the actual problem you're trying to optimize, okay? That class, again, has pretty much one method, which is compute the fitness of a given candidate solution. All right? But I want to be able to change it. And I want to be able to put in my configuration file the name of the problem I want to solve. So with what you guys know so far, this means a bunch of if statement and switches. Okay? Again, as soon as we are done with the next 1 or 2 sessions, we are going to solve that kind of problem with metaprogramming. We are going to make it so that you are going to read this configuration file, and those names here, basic evolutionary algorithm, binary fixed vector, 1 max, well, they will correspond to class names. So I can say at runtime, I can put in a file, a configuration file, the name 1 max, and when my program starts and read that configuration file, it's going to recognize the name 1 max and say, I have a class somewhere called 1 max. And I'm going to use that class to create instances of the problem I'm trying to solve. Okay? So that's something that I would say most of you, at least half of you, should not be able to do right now. Okay? So that means that for right now, for the first version, put that in the configuration file, but you can hard code everything. You can just, apply algorithm only with 1 max. And then when we add another problem or when we do the metaprogramming chapter, okay, we are going to learn to do a little better. And I'm going to explain to you through slides, how to do it, obviously. Breeding method, so that's the selection for breeding. So there are 2 different techniques that are really basic. So I just froze the name here, but I want you to implement the tournament one, okay? So I would specify again in a configuration file which one I want. If I specify tournament, then I can specify the tournament size, the value for k, Okay? Mutation method, I already illustrated those two methods. Okay? The per gene means that you go over every bit of a candidate solution, and with a certain probability, let's say 1% or 2%, you flip it. That's mutation per gene. So you need a mutation rate. Okay? For example, here, 5%. There's another mutation method that actually leaked in the slides already, so I'm going to go ahead and mention it. The per genotype. Genotype means, it's just jargon. Genotype means just a candidate solution vector of bits. Okay? So that means that instead of going over every bit and deciding with a certain probability if you flip it or not, what you do is you say, I'm taking one candidate solution and I will flip one bit, always. I choose it randomly, and that's it. Okay? So two different methods of mutation. Crossover is going to be, the parameter for the crossover method is going to be a number. That number right now is going to always be 1 because we are going to implement 1 point crossover. And then later, if that helps us study some of the OOP technique, I will introduce the other method. And crossover has also a probability. So when you have your two parents, and you have, let's say, a crossover rate of 0.8, which is 80%, 80% of the time you are going to apply crossover. 20% of the time you just let them be and move directly to mutation. Everything is stochastic, everything is random in that algorithm. And then replacement method, we talked about that. We could use, again, a K-tournament. That's very feasible. Right now, we're going to implement something simpler. We're just going to take the worst fitness individual out of the equation. Okay? And if we were implementing tournament, then we would need tournament size. So this is, the names here can all be modified. I don't care. Okay? What I care about is giving you an idea of exactly how flexible this algorithm will have to be by the end of the semester. Okay? So that's going to influence your design. I don't want you to waste your time implementing, both tournament and roulette wheel, but I want your design to be able, for me, to come in and implement, for example, a roulette wheel selection and inject it into your code somehow. So the only thing that matters for you among all those methods is I explain one of each, and you have to know that there are different variants and they need to be plugged in into your code as easily as possible. Other point of detail, let's be civilized. So, and I say that because when I first implemented that kind of stuff, I was not civilized at all. I used all sort of method before to finally go and use property file. Java has this great thing called a property file. What you see here is the syntax of a property file. It's a text file. You put a name equal a value, a name equal a value. And each of those name value pair, is used for a parameter or something like that. So there is an API to read property file without you having to do any sort of parsing. Use that. That's going to make your life easier. That's going to probably take you half an hour to read about it, get it to work, okay? But it's worth it because then you can have this file that is read when your program starts up, and you don't have to worry about anything else. Other strong hint, you need a config class. So this time I'm not, if you want to play and come up with a wild design there too, that's fine. I don't see how, okay? I don't see how you can get this thing working without a config class. A config class is a class that's going to, they would call it a Java bean. It's just there to read, the property file and have all of those left names as fields and store the value in there. And it has to be accessible from everywhere in your code. Okay, every single new operator that you design, like the mutation operator, need to be able to look up in the config class what is the mutation rate, maybe even what is the mutation type that you want to apply. Okay, so what we are going to do for that, and that's how I'm going to finish that presentation. What we are going to do for this is we are going to implement that config class using a design pattern, which is the design pattern I already mentioned previously in the lecture, which is a singleton design pattern. Okay, so the idea is that there's going to be only one instance of that class throughout your entire program, and you are going to have a method, a static method, so a class level method that you can call that's going to return to you always that instance. So the benefit, and why it fits very well here, is that when you guys are writing, for example, let's say that some of you want to have a mutation class, mutation operator class. You are writing a subclass of the mutation operator class, and you need to access the mutation rate. You know it's in the config, okay, or it should be in the config, well, you can just call that static factory method from the class config. The class config is going to be accessible, it's going to be in the same package. By the way, don't go nuts with packages. Keep it simple, okay? That's not really where the design, interesting design stuff is going to be. So you are going to be able to access the class from everywhere. If you can access the class, you can access its static method. If you can access its static method, you can request an instance. And since it's always the same instance, like the same unique instance that is returned, well, everybody will request an instance of that class is going to get the same one. So everybody will get the same config object. Okay, so that's going to allow us to do quick and dirty sharing of data throughout the system. So you guys cannot see that because it's projected on the bottom, but all it says is don't worry about making it thread safe. Okay, like if two parts of your application were trying to get that instance or do something on that instance at the same time, yes, there would be a problem. And there are ways to implement the singleton design pattern so that it is thread safe. For now, what I'm going to ask you to implement is a simple version of the singleton design pattern. Okay, so the code I'm going to show you now is not necessarily thread safe. But guess what? When we get to concurrency, then we are going to make it thread safe. Okay, so just hang in there. All right, here's some code to get you. It's more of an example than usable code directly. It's an illustration of how you can implement a very simple singleton design pattern. And again, not thread safe. Okay, we're going to get there later. So let's say that this is my class config. Okay, I'm having here a static field meant to hold the reference to that one instance that I want to share with everybody. Okay, so it's static so that it's stored as a class level. It's a reference to an object of class config, and I call it unique. Call it whatever you want. Okay, then you can define all the parameters that we talked about that you are using, actually, the population size, max number of generation, etc., as private fields here. And then you have your constructor, load the property file, populate those fields. And then you have here your factory method. So the factory method is also static by definition. It has to be public, otherwise we have a problem. It returns a reference to an object of type config. And all it does is, if the static field unique is null, meaning I don't have an instance yet, I create an instance, I store its reference in the static field unique. And then whether I had to create my first and unique instance or I didn't, because unique was not null, regardless, I return unique. And that's it. Okay? I tried to go for as simple as I could. Again, not thread safe, but it will get you at least started. And this is going to be, yes, sorry, you have a question?
Do we really need the get config method? Could we create static properties in the config class? And like static constructor to
Yes. Yes, you could.
And it will be thread safe? I'm not sure.
Okay, I would have to double check that. I don't know if we go I'm assuming if we go the property way, it's going to be thread safe, because that's Java ways to allow us to implement those kind of things, without doing it by hand. So I don't see why they would not make it thread safe, but I would have to check in the documentation to be sure. That's a good idea. Yeah. So just real quick for the recording and rest. The idea here is that Java also provides you with a concept of property. So every time we talk about making a field, private and defining an accessor, a getter, and a setter on it, okay, what we are doing is we are doing by hand what other programming language do automatically for us as property. The concept of property is I don't care if it's a field. I don't care if it's a method, okay? When I write, for example, my object.x and I assign a value to x, you should be smart enough, you meaning the programming language, should be smart enough to call a setter if I need to. When I say, my value equal my object.x, then you should be smart enough to call a getter. Don't bother me with having to write getX and setX methods, and use that syntax instead. I want to assign thing to x and consider x a quote-unquote property, so that you figure out if you need a getter or setter, or if it's just an attribute that's public. I don't care. That's the idea of property. So if you want to go ahead and try this, it's a good habit to take. Okay, it's a good feature to use. The code on the right shows you how you're going to use this, okay, from anywhere in your code. So you have a config CFG. That's your reference to the unique config instance, and then you just call class name dot name of the static method, and you get your instance, okay, from anywhere in the code, and that's it. All right, so we are done with this. A quick remark. Yes, this is very open-ended, okay? I'm mentioning that again because I had some question by email already about this practice project, especially from the undergraduate section. And yes, it's really open-ended, so it's a difference from the traditional, practice exercise that you get. But that's because we want something larger. We want something that is complicated enough to warrant applying the technique that we study. And the technique that you study in object-oriented design or object-oriented programming, they are not meant for Hello World. You can get them to work to make a Hello World, but then the problem is the opposite. Instead of students saying, well, the application domain is complicated, but now I see why the techniques are valuable, the reaction, the result is the opposite. People say, yeah, I understand what you're doing, but I have no clue why you're torturing us with all of those techniques to just do Hello World, right? So we have to strike a balance, and this is meant to strike that balance, okay? If you have any question, any problem with understanding the Bayes algorithm, I don't want you to waste any time on that, okay? The forums are not really used, okay? I can tell you in the free section, the online section, the face-to-face, and the online undergrad section, those forums are underused. The TA right now is underused. I see people every week in my office hour. I'm glad, but you guys need also to go to the TA online session. You need to ask questions in the forum. There's not enough activity right now, okay? My guess is that most people didn't even get started on that yet. Well, granted, we had a week that was a little special last week, okay? So I'm not blaming you for that week. But what I mean is that get started on that as soon as you can, okay? Start practicing. As we are learning new stuff for metaprogramming in the next sessions, we are going to immediately apply it to that, okay? So you need to get started and ask for help. It's not meant to, to be like, okay, here's a project, now you're on your own. No. We are here to help you. But you need to come to us or send an email or do something, right? Otherwise, we're not going to drill into your mind, anything forcefully. Okay, so we are done with this. I'm going to stop the recording now. If you have any question, let's address them while I switch to the next recording.